Hello, this video is about Calculus 2 centers of mass and moments. These two concepts, when introduced in class, are a little arcane, and the formulas particularly are not intuitive. So, in this, I would like to first go over moments, and talk about those from a statics perspective, and then derive the center of mass. In this video, we'll talk about both statics and Calc 3 techniques, but they're not that difficult, and I think they serve to give a deeper understanding of what's actually going on here and how we get the formulas. So do not be afraid. All right, our X bar and Y bar. I expect at this point we're probably pretty familiar with these formulas, but I also suspect we're asking ourselves where these formulas actually come from, because in class they're often just given to us with little explanation about where they come from. So let's put these guys up here for now. And we're going to start with the moments. And for these, we're given these two formulas instead. The Qx and the Qy, confusingly, the moment for y is based off of x bar and the moment for x is based off of y bar. So let's talk about moments as they appear in a physics context. If you've taken physics 1, you might have seen something like this, where we talk about moments as rotations around a point. If we have a beam here that's fixed at this point here, there's a force acting perpendicularly on the end here. We'll call this 5 newtons. The moment around this point is the torque, or the rotational moment. And if we say that this beam is 4 meters, then that moment is just equal to our force times distance. So m equals 20 Newton meters. So now that we've talked about moment around a point in the physics perspective, let's turn that into moment around a line or moment of area in a statics perspective, and what we really end up talking to about in Calc 2. Before I draw anything and talk about it, just imagine that your plate, our area, if you're trying to find the center, one of the best ways you can do it is to make sure that the rotational moment on one side equals the rotational moment on the other side. But to do that, there's got to be a uniform force on the entire area of the plate. So keeping that in mind, the way I imagine the connection between this moment and that moment is by imagining the area is a uniform force downward. So if I'm just pushing uniformly on that area, that is the force component. Force and area are related to each other. So if I give this like some 3D look to it, okay, that's our new axis, which I'm not going to label. Then this area, or I should do that in red. Then there's a force acting on the area, or there's a force for that area. So yeah, that's our force. It's going into the plane like that. Then where's our distance come from? Well, if we're looking at qx, our moment about the x-axis, I imagine our centroid somewhere about there. This is our distance to the x-axis, right? It's that y bar distance. Y bar, x bar. So in this way, we actually really have the exact same problem. We're saying that, okay, well, if we have this force that's acting uniformly on the area, we can represent that force as coming straight out here. That's the sum of all of the forces on here and acting just at the centroid. And then we have this x bar here, right? And these are going to be orthogonal, perpendicular in the x force direction. And we basically just have the same formula. So we've turned it from being the moment around a point to the moment around this x bar with a little bit of change. We're sort of assuming that this force is acting uniformly on the plate and that this x bar is our distance. And that's how we arrive at the same physical understanding of what's happening between these two formulas. All right. So I hope that sort of clears up about any confusion about what the moments are exactly and how they relate to the physics understanding of a moment around a point. So let's shelve that conversation for a little bit. Let's talk about how we get to x bar and y bar. So from our moment formulas, we can rearrange them so that we say that qx times 1 over area equals y bar, and qy 1 over area equals x bar. If we have, so yeah, now we're searching for these guys. If we have some arbitrary area like this, how am I going to find the centroid of it? The simplest answer is we say we take the centroid of each differential area. Center of each differential area, each tiny square, infinitesimally small square, is literally just the center. So x bar equals 1 over a integral x dA. The reason that makes sense is this is just our x value at that point. And I'll give this x. That's our y-axis. Our y bar, 1 over a integral y dA. This is pretty cool too, just tying this back to our moments, is this actually makes a lot of sense about how this is our moments. We're saying, okay, this is our distance here, and we're pushing down. That's our area. So yeah, same connection, right? We've shown same connection. We've shown again in slightly different language that we have a distance and we're pushing down on this area, except this time we're just integrating it, right? So that's why it's a little different than our just straight up uh, multiplying example, right? All right, that's all well. That makes a lot of sense. How do we turn this from a Calc 3 question into a Calc 2 question with techniques that we can actually solve this with? Because keep in mind, we don't know what dA is. dA is actually, I might draw it like this over here. Ooh, a great square. Keep in mind that dA, this is our differential area, is a multiplication of dx times dy. Like I said, this is this Calc 3 concept that we're sort of butting our heads up against. And don't think about it too hard unless you want to, but it's not that difficult to think about. Because yeah, dA just equals dx times dy. So the result of that is this will end up becoming 1 over a double integral x dy dx. And we'll get to this in Calc 3. I'm sure you'll master that topic and do great at it. But for now, we just want to think about things in terms of single integration. And frankly, this actually, in thinking about it in terms of single integration, makes this problem easier because we only have to do one integral. Doing the double integral can get some complicated and hard. That being said, it does allow us to work with these funky sort of shapes, but for now, we don't need to worry about that. So let's simplify a little bit. This is our shape, much simpler. Could even pretend it's something like, y equals square root of x, right? We'll ignore that for now. Our differential area can be expressed slightly differently. Like I said, we're used to seeing dx's. So let's work with that. This is our dx. We can create a new dA that's based off of the height here. So this is our y. Then we can say that dA equals y dx. You might be sort of starting to see how these guys populate into these equations. And if we're looking for the centroid, then the centroid of a rectangle is just going to be y over 2 and x, right? So if we take those original formulas, we're saying that x bar equals 1 over a integral x dA, and we have this new definition for dx, and we can just substitute that straight in. Integral x y dx. And check that out. What is y but our function? Equals 1 over a integral x f of x dx. I'm running out of space a little bit there, but we can replace it with that definition at that point. We've derived that. Awesome. Let's check it out with y bar. Y bar, as we were saying earlier, equals 1 over a y dA. So let's replace it, because that equals 1 over a integral y times y dx. And again, that's just our y squared there equals y squared. So that just equals our formula. Or forgive me, actually. Yeah, this is y over 2 in this case, right? Because our original y bar is in this equation. But once we turn it into dx, this becomes y over 2. So let's do it in y bar then. Y bar equals 1 over a integral y dA. And now, in this simplified form, we have 1 over a integral. And remember, our new y here is y over 2 times y dx. And check that out. These two y's, those will combine together to give us our y squared. And this 2 is going to come out because that's just a constant. 1 over. So 1 over 2a integral f of x squared dx. And we've arrived at the same formula. Wow, that's pretty cool. So that is the derivation of these two formulas, right? How we get from that. And keep in mind how this connects to the moments. There still really is just about the same thing, because this part here is just another way of talking about this distance here times the area of, or the force of pushing onto that area uniformly. Same thing. Same thing for y, right? This distance, that area that we're pushing down on. So yeah, I said too I wanted to talk a little bit about where we see some of the applications of these things. Like I said, you'll get to this in statics. These deal a lot with statics, and there's actually some kind of cool applications of it. For example, this shape here, if we find the centroid, we'll say it's something like this, right? X bar, Y bar equals our centroid. We can actually use this to figure out the surface area of revolution and the volume of revolution. For volume, the Pappus Goldenus theory says that the volume is equal to area times 2 pi y bar, which is pretty cool, right? So we're just saying that, yeah, if we take this average here, we can multiply it by this area and 2 pi, and that gives us the volume, same as we would do a regular integral. So that's a cool application, and that is, of course, how we can get to, like, if you're trying to figure out surface area of something to paint or volume of a strange shape for manufacturing purposes, that can be pretty useful. Um, so you will see this come up in statics once again, for sure, and somewhere else too. All right, thank you so much. Have a good one, and good luck with your Calculus 2 studies.